Today we're going to start talking about limits and co-limits. Limits and co-limits are a kind of universal object in a category. And one of the things that we like doing in category theory is identifying things with universal properties. Universal properties are when things are somehow the best, or the biggest, or the smallest, or the most canonical, or free, or something. So you look at objects of a certain kind, you find the best one out of all those ones, and the way you say best is you say it's got some kind of universal property, which usually means for any other object of that type, there's some kind of good relationship between them, as we'll see. The most basic kind of limits and co-limits are the ones we'll do first, and these are terminal and initial objects. So let's start with a category C. Let C be any category. We'll start with terminal objects. A terminal object in C is some object T. So it's an object and now it has a universal property. And what's its universal property? Its universal property is, here's your universal object, and we're going to say that given any other object in the category, there is a unique morphism to the terminal object. That's why it's called terminal. Everything kind of ends up there. So it's an object T such that for all x in C, there exists a unique morphism from the other one to the terminal one. That part, the such that part, is the universal property. So this is the, let's see, maybe I'll put it in blue. This part is the universal property. The part saying, among all objects, this one is the one that has a unique morphism going to it from everything else. Incidentally, these are also sometimes called final objects. So let's immediately have some examples. In the category of sets, any one element set is terminal. Any one element set is terminal. Because if you have a set with one element, then there can only be one morphism, one function from any other set to it. And there is precisely one function, because you just send every element of this set to the unique element of this set, and that's the only thing your function can possibly do. So, for example, the set containing 1 is terminal, but also the set containing 4 is terminal, and also the set containing 3,649 is also terminal. It doesn't matter what your element in there is. As long as there's only one element, precisely one element, then it's terminal. Now, one thing you'll immediately notice from this is that there isn't only one terminal set. However, all these terminal sets are really very similar to one another. It doesn't matter what the one object is. And what we're going to see later is that when you have limits and co-limits, there's a certain sense in which they're not precisely unique, but they're unique up to unique isomorphism. Now, uniqueness up to unique isomorphism is a very important notion in category theory, and it's a sort of categorical uniqueness. We're not interested in things being literally unique, because that would be saying something about equalities, and we're supposed to consider isomorphisms to be sort of like equalities. So we're supposed to consider two objects as being more or less the same if they're isomorphic. So that means that we're not looking for uniqueness on the nose, we're only looking for uniqueness up to isomorphism, but not up to any old isomorphism, up to canonical isomorphism. So here, there's a canonical isomorphism between any two of these sets. And we'll prove in a second that terminal objects are unique up to unique isomorphism. So let's have another example. In the category of groups, the trivial group is terminal. Another other example is that in the category of topological spaces, any one-point space is terminal. And it's sort of a little bit pointless to think about how many different trivial groups exist and how many different one-point spaces are terminal, because we don't really care what the one point is when we have a one-point space. There's just one point, which is sort of just exactly the same as the one-element set. It's just saying that all the different one-point spaces are so canonically isomorphic that we can't even be bothered to think of them as different. And what other example could we have? Oh, we could think about a poset. So in any poset, so remember, we can think of a poset. I haven't really got space down here. Can we see that? Let's see. Yes, I think we can. In any poset, regarded as, well, we've got a morphism A to B, which means A is less than or equal to B. So what will it mean to be terminal? Well, it means given any other object, all morphisms between objects are unique. So we can ignore the uniqueness part. Given any other object, there's a morphism to that one, which means that that one must be maximal. Must be the maximum. In any poset, the maximum element is terminal if there is a maximum element. So not a kind of local maximum. I've forgotten what these things are called. Perhaps I should move swiftly on. If there's one element that's greater than or equal to all the other elements, then that one is going to be terminal. Okay, let's move swiftly on from that. Let's prove that terminal objects are unique up to unique isomorphism. So here's the lemma, which is very important. Terminal objects in a given category C are unique up to unique isomorphism. So how do we say that literally? We say if T and T inverse are terminal, then there exists a unique isomorphism T goes to T primed. And what we do here is we do what John Byers sometimes calls the gunslinging contest. So we say it's about who's the fastest gunslinger. So if you have two people who both claim they're the fastest one, then you have a competition between them. So we're going to have a competition between these two terminal objects. And we say, well, this one is terminal, so there's certainly a unique morphism going from this one to that one. But this one is terminal, so there's a unique morphism going from this one to this one. So we've got something that might be an inverse for it, but this one is also terminal, which means that there's a unique morphism going from it to itself, which must be the identity, which means that when we compose like that, then we must get the identity, which shows that that really is an isomorphism. And likewise, if we start there and compose in this direction, then we get something that has to be the same as the identity, because this one is terminal. So I'm not sure if I have long enough actually to write this up, but let's try. T prime is terminal, so we get a unique map from T to T prime. This is the proof. T is terminal, so we get a unique map T prime to T. Let's call that F and G. And finally, we can show that FG equals GF equals 1 since T and T prime are terminal. I have to stop. Last time, I sort of hurried over the proof that terminal objects are unique up to unique isomorphism, and so what I want to do this time is do it properly. So what we've got is T and T prime, both terminal. And what we want to show is that they're uniquely isomorphic to each other. So the first thing we do is say, since T primed is terminal, we have a unique morphism from any object in the category 2T primed. In particular, we have one from T. We have a unique morphism from T to T primed, and we can call that F. But since T is terminal, T is terminal, we have one going in the opposite direction. We have a unique morphism from T prime to T, and we can call that G. And now the idea is to show that F and G are inverse to one another. So now, since T is terminal, we also have a unique morphism from T to T. Unique morphism from T to T, and it's the identity. Which means that any other morphism from T to T has to be the identity. So in particular, this composite, so in particular, the composite start at T, go to T prime, and then go back to T, has to be the identity on T. And similarly, since T primed is terminal, there's a unique morphism from T prime to itself. We have a unique morphism T primed to itself, and that has to be the identity on T primed. And so in particular, the composite where we start at T prime, go to T via G, and then go back to T prime via F, that has to be the identity on T prime. So we've composed F and G both ways round and achieved the identity in both cases. So this exhibits an isomorphism. So we have that G composed with F is the identity on T, and F composed with G is the identity on T primed. So that gives us the unique isomorphism between T and T primed. Now this is a sort of prototype proof for all the later proofs that limits and colimits are unique up to unique isomorphism. So that's quite important. Now we've already seen, one thing we've already seen is that, we've now seen that terminal objects aren't unique, they're only unique up to unique isomorphism. But another thing that's true is that they don't necessarily have to exist. So we've seen terminal objects in set, in group, and in top. So here's a category without any terminal objects. There are various ways in which you can fail to have a terminal object. For example, here are some non-examples. So we can have a very small category with two objects and a pair of morphisms that are not equal. So there's no terminal object here, right? Because neither object has a unique morphism from every other object to itself. So this object has two different morphisms going from here, and this object has no morphisms going from here to here. So this has no terminal object. Here's another way you can fail to have no terminal object. For example, you could have 4 objects and some arrows like that. So this object, none of the objects has a morphism from all the other objects to itself. Okay. Another way in which we could fail to be terminal is you could have some kind of long string that keeps going of morphisms that just keeps going and going and going. That is also going to fail to have a terminal object. Before I draw this line, another very interesting one that fails to have a terminal object is the category of fields. Because unless you allow for a one-object field, which some people sometimes do, but usually we don't allow for a one-object field because we usually say that 0 in the field can't be equal to 1. And that means that it can't be a terminal. It can't be terminal. I mean, this isn't a proof, right, but it's kind of the idea behind it is that if you've got at least two objects, supposing you're trying to map from some other field to there, well, you don't know whether you're going to send each object to 0 or 1. And so the category of fields does not have a terminal object. And this is sort of indicative of fields being a tricky category. We'll later see that many of these categories I've just talked about are certain kinds of categories. They're monadic over sets. Which means that they can be expressed in terms of monads. If they can be expressed in terms of monads, they can definitely, that means they definitely have limits, and in particular they'll have terminal objects, because terminal objects will turn out to be a kind of limit. So when you don't have a terminal object, then that means you've failed in that sense, and you can't possibly be monadic. Now I'm getting a bit ahead of myself, so I'll stop there, and next time we'll talk about the dual notion to this, which is the notion of initial object. Today we're going to talk about initial objects. Initial objects are just the dual of terminal objects. There, that's all you need to know. Because now you understand everything about initial objects, right? Okay, I'll explain what that actually means. Of course, dual means that if you turn around all the morphisms in the definition, so if they went from there to there, we're going to make them go from there to there now, then you get the dual notion. So what does that mean in this case? Well, remember that a terminal object was an object such that given any other object in the category, there was a unique morphism to this object. So an initial object is going to be an object such that given any other object in the category, there's a unique morphism from the object. So we just turn the arrow around. So let's write down the definition. An initial object in a category C is an object I such that, well, what's the universal property? The bit that comes next is the universal property, such that for all objects X in the category, there exists a unique morphism from our initial one to our other one. So it's the kind of starting point, because it's initial, right? So notice that if we turn around every arrow in this definition to face the other way, there's only one arrow, so we turn this one around and it would become exactly the definition of terminal object. Which means that an initial object in C is precisely a terminal object in C op. Right. Let's immediately have some examples. Before we had the category of sets, we can look at the category of sets again, and this time it's going to be the empty set. Because given any other set, there's a unique function from the empty set to this one, because there's nothing to do, right? There's only one thing you can do, because there isn't anything to do. It's that curious empty function. In set, the empty set is initial. In the category of topological spaces, it's the same thing. Empty space is initial. In the category of groups, something a bit different happens, because of course you can't have an empty group. The group must at the very least have the identity in it. So the identity, the group with just the identity in it, that's the trivial group, is really the smallest group you can have. Now that certainly is initial, because given any other group, there is a unique morphism, homomorphism from the trivial group to this one, Why? Well, you've got to send this element somewhere, but it's the identity, so it has to go to the identity over there. There's no choice in the matter. That's absolutely the only thing you can do. So in group, the trivial group is initial. And remember, the trivial group was also terminal. So in fact, in groups, the trivial group is initial and terminal. This is not always the case, right? In set, it was a one-element set that was terminal, and it's the zero-element set that is initial. And so in set and top, they're different, whereas in groups, they happen to be the same. And this is actually a very useful property about groups. And so sometimes it's given the name null object, which means it's terminal and initial. There are other categories with objects that are terminal and initial. For example, if you think about the category of pointed sets, a pointed set is a set with a chosen element, the point, and the morphisms between them have to take the chosen element to the chosen element, so they're sort of base point preserving. And also you can think about base spaces, which are likewise, a base space is a topological space with a chosen point, called the base point, and the maps between them are then continuous maps that take the base point to the base point, right? So now, in both of these cases, the smallest object you could possibly have isn't empty anymore because it has to have a base point. So the smallest object you can have is the one with just the base point and nothing else, in which case it's initial, just in the same way that the trivial group was initial. Because if you've got a base space with a base point and nothing else, if you try and map it to another space, there's only one thing you can possibly do, right? Because the base point here has to go to the base point there, so you have no choice in the matter whatsoever. So the set or the space containing just the base point is initial, and indeed also terminal. So that's quite interesting. Another example that I didn't talk about last time is the example of categories themselves. We have terminal category and initial category. Another example is in cat. We have the empty category. Is initial for just a very similar argument to the one that says that the empty set is initial. And for the terminal category, we have any one element category, a category with one element, precisely one element object and one morphism. Of course, if there's only one morphism, it has to be the identity, right? So that's got to be the identity, is terminal. Because if you think about a functor from any other category to this one, there's no choice about where you send the objects, because they've all got to go to the one object here, and then there's no choice about where to send any morphisms either, because they've all got to go to the single morphism that's here. So that's what happens in cat, and it's also worth noting that in the category of fields, we have no terminal object, and we also have no initial object. This whole thing is a problem about different characteristics, incidentally. Right. So it's worth also saying, while we're here, that anything that's true about terminal objects is going to be also true about initial objects in the dual form. Because an initial object in here is just a terminal object in the dual category, anything we can deduce about terminal objects, we can just then dualize and deduce about initial objects. So, for example, initial objects, just like terminal objects, are unique up to unique isomorphism. Unique up to unique isomorphism. And the proof is exactly the same as the one for terminal object, and it's the dual. Finally, a bit of notation. Terminal objects are often written 1 and initial objects as 0. Can't spell. Initial objects as 0. And for future reference, note that terminal objects are a kind of limit and initial objects are a kind of co-limit. So we'll see what that means later.